Swayam Prabha. Digital India. Educated India.
Once again, let me continue the shear strength. In my previous lecture, I was giving behavior of soil under shear and various aspects I have shown, and few more things I would like to show. So, let me go the first slide. This is the one the under unconfined compression test, how it will be. As I have mentioned that unconfined compression test is the special form of triaxial test. That means, your sigma 3 is 0 here, and if this is sigma and unconfined compression test also we supposed to do on saturated soil, and if you do that, and then you will have sigma 3 is 0 and sigma 1 here is nothing but sigma 1 is q u, that is if you go to a stress strain curve and we get the value that is actually say q u ultimate shear strength, and that is sigma 1 q u u nothing but sigma 1 and sigma 3 is 0. So, based on this sigma 3 equal to 0 and sigma 1 equal to q u, if you plot the circle, if you make the Mohr circle and then Mohr circle, this will be supposed to be unique circle, if you because only one circle we can get, and there will not be any phi, and so your that means your shear strength will be constant, and then your envelope will be horizontal like this, and if it is so, then your Cu under strength from the unconfined compression test, suppose whatever you get Cu, which will be nothing but this diameter, half of the diameter, this is radius, and so this is diameter. So, diameter is itself here is sigma 1. So, radius will be sigma 1 by 2, and so that means Cu equal to sigma 1 by 2, and this is nothing but q u by 2. So, that means from shear strength result under strength test, if unconfined compression strength is given in some problem, many competitive exam, some problem will be given, instead of giving the shear strength parameter, they may give unconfined compressive strength is given some value. Then what you have to do, you have to take the shear strength parameter from there, which will be nothing but Cu equal to q u by 2. So, many times students take whatever is given, that itself is Cu, and then everything will go wrong. So, that is also another important point you should remember. Now, stress strain relationship for different soil, and you can see here generally we have different convention for plotting different test results, and a stress strain relationship can be from the results of triaxial test or direct shear test or compression test, any test we do, and results are plotted in the form of shear displacement. Direct shear test, actually in the direct shear test, it is plotted shear displacement x axis and shear stress is y axis, and in the triaxial test, one axis is deviator stress, other axis is axial strain, and for unconfined compression test it will be axial stress and other is axial. So, this instead of sigma 1 minus sigma 3, it will be axial stress. So, it will nothing but sigma 3 is 0 is nothing but sigma 1. So, that is why. So, now this is a figure presented here with stress strain behavior of 3 different soil, and you can see first one, this is the one, this one is undisturbed sensitive clays. Sensitive clays, when it is undisturbed condition, if you test, you will have a prominent peak with at a very low strain, a prominent peak stress with at a lower strain, and this one typically can have some failure like this certainly, and second sample is remolded sensitive clays. So, in the sensitive clay if remolded and sample is prepared and tested, then it will be stress will be increasing, the stress there here actually stress will be increasing gradually, much more gradually with increase of shear strength compared to this. This here actually shear strength with the shear strength versus increase of shear stress is quite rapid, whereas here with the increase of shear strength increase is quite slow, and it you can see it will be continuously extend, and it may not show any prominent failure, and that means how to decide that whether test is completed or not. So, that when this behavior occurs, that time sample shape take like this barreling, that means it will shorten and it will laterally expanded. So, that is called barreling happens, and how much we allow. Generally, to terminate the test we generally 15 to 20% strain, if it exceeds that 15 to 20% strain, then we terminate the test and we consider that as the failure. So, if barreling occurs, that means we allow maximum up to 15 to 20% strain and then you terminate the test. And similarly, there is another sample, that is third one, that is insensitive clays, and it will be it will have a comparatively increase of stress with increase of strain greater than this one, but lower than this one, and it will be reaching to a peak, then it will be sometime decrease in value or it will may continue constant. So, that is another type of soil, that is insensitive. So, that means if this type of sometime in a competitive exam, this type of graph will be given and 1, 2, 3 is marked, and then there will be several combination will be given, what is what actually you have to identify. So, if until unless you know the behavior of the soil, stress and behavior of the soil for different condition, you will not be able to identify. So, that you have to understand properly. This is actually for undisturbed sensitive clay, this is a remolded sensitive clay, and this is a insensitive, the normal soil. And now, as I have mentioned at the beginning, normally consolidated and over consolidated, you can see here when normally consolidated soil you test axial strain versus shear strain, that will be a continuous increase and of David's stress with the increase of strain, and it will be reached to a peak and then it may continue keep constant or decrease little, whereas for over consolidated clay it will be increase the stress with the increase of strain sharply, reach to a peak value and then it will be going down. And so, the over consolidated clay shows a greater strength than a normally consolidated, that obviously strength this is a greater strength than this, and has a pronounced peak, it has a peak, but it does not have any peak, and the stress falls off as strain increases. That means, beyond this if you increase further strain, then the stress strength value reduced, and that phenomena is called work softening. And this is one thing, and then while shearing also normally consolidated soil generally continuously decrease in volume. As a result, so volume decrease will be there. So, if this is the zero change, zero reference, then if you axial strain versus volume change, if you observe for normally consolidated, it will continuously decrease in volume. Whereas, if it is over consolidated clay, initially it will show some decrease in volume, but after some time it will continuously increase in volume, like a behavior dilation in sand, similar type of things happens here. And the reduction in the value of shear strength from a peak value to a residual value when large strains are applied to over consolidated. Over consolidated typically whatever we have shown there. So, it will reach peak after reaching the peak, and if you apply a large strain, then it will fall and reach to a value that is called residual strength. And since during the shearing there is a volume change is taking place, and we have seen for normally consolidated it is continuously volume decrease. If the volume decrease, then what will happen? Pore pressure will be positive. So, that is what it is happening. If you pore pressure measurement you do normally consolidated test during shear, then your pore pressure will be continuous increase like this, whereas if you observe for a normally over consolidated clay, there actually you have seen that initial strain strain level due to initial straining up to some percentage, the volume will be decreasing. So, there also pore pressure is positive, but after reaching to a certain value of axial strain, the volume increases. So, that volume increase actually, since volume increases, your pore pressure will be negative. So, that is what if it is a over consolidated clay, this is the pore pressure measurement during the shear. If you do, there will be initial increase positive pore pressure, and then at some time there will be continuously negative pore pressure will be observing during shearing. And effect of strain rate, that is also another when we talk about the shear strength, so triaxial test or unconfined compression test or direct shear test, anywhere you do, always we maintain a particular value of the strain rate. And what is the effect of strain rate, change of strain rate? These are the several things that is the undrained strength of a clay is known to be affected by the rate of strain or rate of shear. The undrained strength increases with the increase in rate of shear. So, that is the observation. Undrained strength increases with the increase in the rate of shear. And what rate? Some report, some scientists actually or observe, they have a researcher, they observed this Casagrande and Wilson, they have reported that this increase can be up to 40 to 80% when a soil sample is strained sheared suppose 1 minute and 30 minutes. If one sample is sheared at within 1 minute, another sample is sheared by 30 days, it is so slow. Then because of this change of rate, that increase in shear strength can be up to in the order of 40 to 80%, but different soil will have different increase. However, the small variation from the normal laboratory test actually we recommend some value of strain rate, but if there is a small change, minor change, that actually may not affect the test. However, difference in rate of shear, that means whatever shear rate is in the field and actual field, and whatever shear rate or strain rate you apply during the test, if they are significantly different, then your undrained strength will be appreciably different value will observe. So, that means you need to maintain the strain rate expected during the failure in the field. Same strain rate if you maintain in the lab, then only that value will be useful for the calculation. So, that is the thing you have to keep in mind. Whereas, you can see where is a CD test, that means consolidated drain test, if you do in that case generally that hardly there is any effect on rate of strain. So, strain rate does not have much effect on CD test. So, these are the few observations, that means with the change of strain rate there is a increase of undrained strength we observe, and whereas in the CD test generally there is no change, and in between some qualitative information how much change, that means 1 day to 30 days, that means if you have same sample if you shear by 1 day and another sample you shear over a period of 30 days, then increase in strength can be in the order of 40 to 80% depending on the soil. So, these are the important point which can be noted for effect of strain on shear test. Similarly, stress strain and volume change the behavior of sand, whatever we have discussed for clay, and that to be that to normally consolidated, over consolidated, different clays will behaving differently. that we have seen. Now, here actually for sand also you can see that sand again like clay we have differentiated or divided into two group, one is normally consolidated, other one is over consolidated. Whereas, here sand actually classified dense and loose, there can be in between also, but if it is extreme dense sand if you test and extreme loose sand if you test, and then we will whatever stress strain deviator stress versus this is the deviator stress and this is the axial strain. If you plot, then this test actually for sand it will reach to a peak at a certain value of strain, and then finally, it will be decreasing and reach to a constant value after a significant high value of strain, this shear stress or deviator stress to reach to a constant value, and that is called ultimate stress for that sand. And if you test a loose sand, similar condition loose sand, if you apply deviator stress and you apply same confining pressure and strain it, then you can see that the increase of deviator stress or deviator stress required to strain with the increase of axial strain, deviator stress increase is very quite slow and it will flat, and finally, at a large value of strain it will be also meeting to the value for a peak ultimate stress of the dense sand. So, you can see it was peaking reaching to peak and then dropping to a constant value, and it is continuously increasing and it finally reaching to the same value. So, this is the behavior of shear stress behavior of the loose and dense sand. And now, another observation is we have seen already that your loose sand when subjected to shearing load, then what will happen? It will continuously volume change will take place, and that will be you can see volume decrease for loose sand continuously volume decrease, and for whereas for dense sand it will be initially up to certain strain value this volume decrease will be there, but when it exceeded that strain value, then it will have volume increase, that is dilation, because dense sand will have dilation effect. So, this will be increase in volume, and this behavior is, so that means dense sand behavior is almost like almost similar to over consolidated clay, and loose sand behavior is similar to normally consolidated behavior. Now, another observation is that we have mentioned that critical density, where if you during shearing neither it goes undergo volume change increase or decrease, neither increase nor decrease. So, that is called critical density, and corresponding to critical density we get the critical void ratio. So, here actually if you consider a loose soil, the initial void ratio may be here, that is E lowest or loose, and when you shear continuously at different stages its void ratio will be decreasing, because this volume is changing means voids is reducing. So, void ratio automatically becoming smaller. So, it will be with shear strain value void ratio will be decreasing, but that decreasing and at a large strain value the value become that will be void ratio will become constant. Similarly, for dense sand it will have a very low value of void ratio, dense sand means void is less, and as we see that at the initial portion of the shearing it volume change volume increase happens. Because of that void ratio also will decrease up to some point, and then further increase of strain the volume will be increasing. When volume increasing will be there, then your void ratio again will be increasing. So, that because of that from here there is a upward direction upward movement of the void ratio plot, and finally, it will reach to a constant value, where it will be reaching loose sand when is a large strain whatever value it reached, dense sand also at a large strain will reach to it will value will be reducing, but finally, it will reach to a stable value, and that value is nothing but the critical void ratio. So, this critical void ratio also can be obtained from the laboratory by some mechanism, and that we can see in the next slide. You can see here that we can see at this point actually no volume change, and if there is a positive volume increase this side and volume decrease this side, if I plot, and this side is initial void ratio. Suppose I choose a initial void ratio very small, and then I apply a confining pressure, certain value of confining pressure, and then I will see the volume change. And if I see the volume decrease, then I will get some point this side, and if I see the volume increase, then I will get a point this side. So, like that for a particular value of confining pressure, I will choose several initial void ratio, and then I will get several volume change, either increase or decrease, and then finally, those points, if the confining pressure is constant. So, for different initial values, initial void ratio values, if I test volume change or measure the volume change, those points if I plot here, those points will be in the same line. And if I join all those lines, it will pass through this line, 0 line. So, when this line is intersecting that 0 line, that is actually critical void ratio. Similarly, now suppose I have conducted this test with a sigma 3 equal to some value, suppose 10 kPa or 20 kPa or 100 kPa. Now, I will do another set of tests with another confining pressure, suppose 200 kPa. Now, again with 200 kPa, I will choose at one initial void ratio, and then I will go up to shear and see what is the volume change. If it is decrease, I will put this side, if it is increase, I will put this side. Then I will take another another initial void ratio, then same confining pressure and go up to the shear and see what is the volume change. If it is again decrease this side, if it decrease this side, like that I can get a number of points, and finally, those points if I see that they will be coming in a straight line, and that straight line when it will join, it will intersect the 0 point at this point. Then that means, the second, suppose it is 100 kPa confining pressure, this is about 200 kPa confining pressure. So, for different confining pressure, we are getting different critical void ratio. So, that means, by changing confining pressure and changing the initial void ratio, we can get those lines, and those lines will be intersecting with the 0 volume change line, and from there we can get the sigma corresponding to each sigma 3 values, I can get the one critical void ratio, and finally, if I plot them critical void ratio versus confining pressure, I will get a curve like this. So, this can be, so critical void ratio is a very important term for sand, where we will not get any volume change. If it is low, if the void ratio is lower than the critical void ratio, then it will dilation will be there, that means volume increase, and if the void ratio is greater than the critical void ratio, then on shearing the volume decrease will be there. So, that is the important observation can be noted. Now, another last I have listed several tests. I have mentioned direct shear test, I have mentioned triaxial test, I have mentioned unconfined compression test, and I have mentioned also vane shear test. So, vane shear test is a very important test, is a field test basically. Why and where we apply this field test actually? Generally, when there is a very soft and sensitive clay, there actually obtaining a undisturbed sample is very difficult, and while if you try to do that, then actually its actually strength behavior will change significantly, and because of that, instead of sampling to that soil, we can directly go to the field and test, and that is the test actually vane shear test, which is suitable for soft sensitive clays. So, this is the same vane shear test. It will have 4 vanes, and it will be welded to a rod, and between two vanes actually there will be 90 degrees angle. That means, we can imagine one rectangle here, this side one and other side one, and these two together when we join one rectangle, the width of the rectangle can be considered as the diameter of the vane, and whereas the vane in this direction depth wise, that is can be considered as a height of the vane. And this vane actually with this connected to the rod with 4 vanes, it can be lowered or pushed inside the soil, and after pushing to the soil, then on the desired depth, and we can through the rod we can apply a torque, and when we apply the torque, then the different places shearing resistance will be developed. So, that shearing resistance can be developed below the vane on the soil, this like this, and shear resistance also can develop above the vane if it is inside the soil deep enough, then before felling that above the surface of the height above the top of the vane also there will be shear, and also cylindrical surface. Suppose this is the vane is rotating, while rotating the soil around will give a resistance like this. So, that will be resistance around this cylinder. So, that is what if I imagine those stress actually, and you can see this whatever cylindric vertical surface whatever resistance, that we can say Cu here, and similarly at the bottom this is actually like a circular shaft, we are applying a torque, and you know that from solid mechanics the shear stress distribution along the it will be something like this. 0 will be here, and at the periphery it will be maximum shear stress. So, that is what at the base or at the top shear stress or shear strength distribution is like this, as a maximum here and minimum here. We can use this, but instead of using this we are considering a average shear strength, whatever is here we are considering soil shear strength, same value here, that is Cu here, that is uniform I will consider at this place, I will consider Cu also here, and if I consider that, based on that I can whatever external torque I have applied and whatever resistance developed, and that can be converted into torque, and that to be equated. From there I can find out the shear strength of the soil. So, I will show those things in the next 1 or 2 slides. So, this is the thing once again I have explained here, this is the vane, and we to apply whatever already all I have told in this one. I do not want to spend much time on this. And this one, this is a see, as I have mentioned that your from the cylindrical surface, this is the cylindrical surface, and when it is vane is rotated. So, along this surface the shear will be there, perpendicular to this the shear will be there like this. So, if I consider shear is Cu undense shear strength, then what will be the force will be there? It is perimeter is pi times d, and then if I multiply it by h, then it will be total surface area of the cylindrical surface. And if you have undense shear strength is Cu, Cu multiplied by surface area will become the shear force. Similarly, in the circular area, if I consider uniform pressure here throughout, and then at a radial distance r, if I take if I consider a annular area. So, it will be its area is 2 pi r into dr, the area is 2 pi r dr, and if I multiply by Cu, then it become force. So, that 2 pi r shear into Cu, this become force, and r is varying from 0 to d. Suppose if the circle is this one, this is 0 and this is d. So, varying. So, I will have to integrate 0 to d, and since resistance come from top and bottom, and if I assume resistance from the top and bottom same, I can after doing this I can multiply by 2. So, this will be the total shear force developed by the vane. Now, but we have applied moment. So, you have to equate with moment only. So, if I want to take the moment, then whatever I have got this one, this is acting at a distance r from the center. So, I will multiply this force multiplied by d by 2, then I will get a torque along the your shaft. Similarly, this is the force and again it is acting at a this is not d by 2, this will be r actually, this will be r actually. So, at a this force was at a r distance, then I will multiply by r. So, I had taken annular ring here. So, this force into this r I will multiply, and then this become torque. Now, this when I am this was force, I am multiplied by r, this become torque. This was force, I have multiplied by this, then become torque. So, this torque suppose is accidentally applied torque, and this one if I integrate and simplify equate with this torque, then I get this expression pi c u d square h by 2 plus d cube by 6, when I have considered resistance from both the surfaces, and where c u is the undense shear strength. And now, if I consider if I ignore the resistance from the top, then your total shear force will be this much, total this much, and this will be once, this will not multiplied by 2, and this will not be d by 2, it will be r actually, this r distance we have taken. And so, again this one if I equate and simplify, then t equal to I will get another expression slightly different from there, because we have ignored the resistance from the top. So, this is the another expression. Next, I can give you one example of this. The problem is the vein of 112 millimeter long and 70 millimeter diameter was pressed in soft clay at the bottom of a borehole. Torque was applied to failure of the soil. The undense shear strength of the clay was found from another test 40 kilonewton per meter square. Determine the value of torque at which the failure of the soil occurred, considering resistance both from top and bottom and from bottom only. So, if I do this problem, it will be very simple problem, just application of, if I consider the first one expression will be T will be equal to pi c u actually 40, and your it will be 0.075 square into 0.1125 divided by 2 plus 0.075 q divided by 6 into 1000 Newton meter. So, it gives you the value equal to 48.39 Newton meter, and for second case actually it will be T equal to pi into 40 into 0.075 square into 0.01 not 0, it will be 0.1125 by 2 plus 0.075 cube by 12 here into 1000, that gives you 44.2 Newton meter. So, obviously, when resistance at the top is not there, lesser torque will be required. So, that is what, when you have considered only one side resistance, you have got the lesser value of torque. So, this is the problem. We have since suppose from some test we have got the undense strength, and we can verify by torque. Generally, we measure the torque. And get the value of c u. Here actually for the verification purpose, suppose c u is known, what value of torque is required, that is suppose we can want to find out. This problem is given in the reverse way. Thank you. So, I will stop here. This is the one I just want to almost clear, almost shear strength is covered. Now, since it is a very important topic, I will take one more module where I will just highlight the important points and summarize the shear strength topic. Thank you.